We said concurrent transactions challenge our ability in maintaining asset properties of the database. So, why do we want to support concurrent transactions? Many database management systems work as the backbone of online services with so many users that submit many requests to the database management system at the same time. There are advantages to processing multiple concurrent transactions at the same time when possible. Concurrency increases processor and disk utilization, and that is an advantage. This is because, for example, while one transaction is using the CPU, another can be reading from or writing to the disk. This increases the transaction throughput. Another one is that when concurrency is supported, short transactions wouldn't need to wait behind long transactions to run when they're finished. Therefore, concurrent transactions reduce the average response time for shorter transactions and therefore, on average, for all transactions. Database management system needs to provide concurrency control in a way that isolation and consistency are maintained. Isolation is achieved by database management system handling the details of scheduling various transactions in a specific order that is called interleaving. The result is executing transactions of each user in a specific scheduled order and getting the result as if they are the only user of the system. Consistency is achieved by database management system handling the details of enforcing integrity constraints so that database stays in consistent state after each transaction. The transactions that run in a database management system need a schedule to gain access to resources to run. A schedule for a set of transactions must include all instructions of the transactions and must preserve the order of those instructions in each individual transaction. A transaction that successfully completes its execution will have a commit instruction at the last statement, which is basically writing the results into the database. A transaction that fails to successfully complete its execution will have an abort instruction as the last statement. But what is interleaving? Interleaving is the need to swap the control of transaction execution between multiple concurrent transactions. For example, executing a few instructions from transaction 1 and a few instructions from transaction 2, and again a few more instructions from transaction 1 and transaction 2, and so on. This action, which might happen for many concurrent transactions, is called interleaving of transactions. As transactions request reads and writes of database elements, these requests are passed to the scheduler. In most situations, the scheduler will execute the reads and writes directly, sometimes calling buffer manager if the desired database element is not in the buffer. Scheduler decides the order of those reads and writes. Let's see an example. This figure shows two different transactions, T1 and T2, with their instructions, reads, writes, and operations on local variables. The first transaction, T1, reads memory buffer location A to variable T, then it adds 100 to variable T, writes it back on buffer location A. Then reads B to variable T, adds 100 to it, and writes it back to memory buffer location B. Transaction T2 reads A to S, multiplies it by 2, writes the result in A, then reads buffer location B to S, doubles it, and writes it back. Let's examine different schedules for transactions T1 and T2 and see if the results could be different. First, we examine what happens if all of the instructions of transaction T1 execute and finish, and then instructions of transaction T2, execute and finish. We monitor the values of A and B throughout the execution of two transactions, as we see here. First, we read the value of A into T. As shown, the assumption is that A has the value 25. So T will have the value 25 now. Then we add 100 to T, so it is now 125. Then we write T to A, therefore A, which is a location in memory buffer, is now 125. Then we read B. B is also 25. We read it to T and add 100 on T. So T now has value 125. Then we write it back on B. And buffer location B now contains 125 then. So by the end of transaction 1, we have value of 125 on both A and B. We proceed with transaction T2. First, we read the value of A, which is 125 now, to S. We multiply it and write it back to A. So A has a value 250 now. We repeat the same thing on B. And at the end of transaction T2, which is the end of both transactions, we will have 250 on both A and B. Now, let's see what happens if we first execute transaction T2, then transaction T1. Going through the same steps in each transaction and the same starting values of 25 on both of A and B, the different order of execution will cause different results. It causes us to first multiply the value of 25 on A and then add 100 to it. So we will have 150 in A by the end of both transactions. The same is for B. In our third example, let's check the results with interleaving of instructions in transactions T1 and T2. Interleaving includes changing the order of transactions so that some of the instructions of transaction T1 are done, then some of the instructions of transaction T2 are done, then the rest of the instructions of transaction T1 are done, and then the rest of the instructions of transaction T2. As you may see, the result is similar to the first schedule, which was the execution of all instructions of transaction T1, followed by all instructions of transaction T2. Can you think of a reason for this? Note to the order of usage of A and B separately in the given schedules. You can see that the order is preserved for each individual location A and B between the example 1 and example 3. Therefore, a similar result. Changing the order of transactions or interleaving transactions might lead to anomalous outcomes or values we did not expect. So, why do we do it then? There are several important reasons. Individual transactions may be slow. Interleaving may avoid blocking other users during slow transactions. This improves performance. Transactions may wait for locks. Interleaving may avoid blocking other users while current transaction is also waiting. This also improves performance. Disk access may be slow. Interleaving may let some transactions use CPU while others are accessing disk. Note that all these reasons are concerning large differences in performance. So we do perform scheduling and use interleaving in a way to enhance performance. However, we have to do it in a way that the desired outcome is correct and consistent.